Hello everyone. Let's continue our discussion on gen clock derivation. So we had a typical scenario over here where your generated clock waveform was something like this. The first rising edge of your gen clock arrived at the first edge of your master clock. The second rising edge of the gen clock arrived at the fifth edge of the master clock. But the middle edge, the fall edge, which is the second edge of the gen clock, it's neither on 2 nor on 3. So how do we code this kind of scenarios? So let's see, what do we have. So we have the gen clock. Over here we have the gen clock name, we have the source and port pin. Let's put it that. So this all we know. The name of the generator clock is gen underscore clock, and its master is master underscore clock. So now what do we have? Let's try to put what do we have. So we have the first edge of the gen clock, or the rise edge of the gen clock, at the first edge of the master clock. So let's put an edge of 1 over here. Okay. Next we have the first fall edge, which is close to your second edge. Okay. The previous edge of this particular edge of the master is the second edge of your master clock. So let's put that over here. Okay, let's put the second edge over here for time being, and the last edge, or the second rising edge, is at the fifth edge of your master clock. So let's put it over here. So now this is where your shifted edge comes into picture. So shifted edge says that this edge is shifted by how many nanoseconds from your master clock. So for example, let's say this is your first edge. This is the first edge of your gen clock. It is not the first edge of your gen clock. Basically, the rise edge of the gen clock is on the first edge of the master clock. Now we have to say that the rise edge of the gen clock is shifted by how many nanoseconds from the first edge of the master clock. And over here the answer is 0. So let's put a 0 over here. Okay. Next, what we have to ask ourselves is the fall edge of this particular gen clock is shifted by how many nanoseconds of the second master clock edge. So the answer is it's at 3 nanosecond, and the second clock edge comes at 2 nanosecond. The answer is 1 nanosecond. So it says that the fall edge of the gen clock is shifted by 1 nanosecond from the second edge of the master clock. Okay. So the fall edge of your gen clock is shifted by 1 nanosecond from second edge of the master clock. Okay. And finally you have the second rising edge. The second rising edge comes at the fifth edge, and it is shifted by how many nanoseconds? It is shifted by 0 nanosecond. So let's put a 0 over here. So this is how you can represent this kind of waveform using this structure, and the rest all will be none. The values for the rest all will be none. So this says that any kind of waveform which is present at the generator clock pin or the generator clock port can be defined with the existing switches that we have, or existing options or the properties of the generator clock that we have. So that is always possible. So any kind of waveform we have been given over here, using the shifted edge and edge combination, or using the divided by, inverted and duty cycle, all these options are just enough for us to represent any kind of waveform that a circuit might generate. Okay, so this was about the gen clock derivation and the shift and the introduction to the shifted edge option. The final one that we have been pending is the multiply by option and the duty cycle. So it's pretty simple. It's not as complicated as we had the previous ones. So multiply by, let's look into a sample circuit. So for example, you have a XOR gate. The XOR gate, one of the inputs of the XOR gate is the master clock. Okay, and the second input to the XOR gate is the master clock, but delayed by 2 nanosecond. Okay, and the combination of this particular thing will create a generated clock out of it. So let's try to first build the waveform. So for example, you have this master clock which is coming at rise edge as 0 nanosecond, the fall at 4, and and the third rise at 0 nanosecond, 8 nanosecond. So for example, this master clock is of a period 8 nanosecond because this is the one full clock cycle. Okay, so the master clock has a period of 8 nanosecond. When we say multiply by, which means the frequency of this particular, let's say this is 8 nanosecond, it will have some frequency, x frequency. The generated clock should be a faster clock frequency. So basically whatever waveform you see over here, there will be smaller waveform which you see over here. Let's try to derive it. So this is the master clock that goes directly to the input of the XOR gate. Okay, and let's draw the delayed master clock, which is at the delay of 2 nanosecond. Okay, so the waveform that is over here, which is the master clock dash, it is at a delay of 2 nanosecond. So this is the waveform that you see at this input. Okay, now XOR. So XOR, if you have one cross one XOR 1 is 0 and one XOR 0 is 1. Okay, so basically all the unequal inputs at the unequal inputs of the XOR gates create a logic 1, and same inputs at the input of the XOR gate creates a logic 0. So if you have similar inputs at the input of the XOR gate, the output of the XOR gate is 0. So let's draw it. So output of the XOR gate is 0. If you have dissimilar logics at the input of the XOR gate, for example logic 1 and logic 0, the output of the XOR gate is logic 1. Okay, so over here you have similar logics at the input of the XOR gate. You have logic 0, logic 0. Output of the XOR gate is logic 0. And again you have dissimilar logics at the input of the XOR gate, which is logic 0 and logic 1. So output of the XOR gate is logic 1. So this is the waveform that you see at the output. Now if you try to calculate the period of this particular waveform, so the period of this is one particular clock cycle. So the period of this clock cycle is 6 minus 2, which is 4 nanosecond, and initially it was 8 nanosecond. So 4 nanosecond is half of 8 nanosecond, so that's why it's a multiply by circuit. Okay, period will get divided and your clock frequency will get multiplied. So now how to code this particular waveform over here? Let's do it. So you have the gen clock, you have the master clock, and you have the multiply by option. You just give multiply by option as 2, and you give the 50% duty cycle. That's all. That's the only option that is needed to define a multiply by circuit. Now for example, if there was a circuit that had created an output waveform with a duty cycle of let's say 30 and 70. For example, the waveform was at the rise edge for 30% of the clock cycle, and was at the fall side for 70% of the duty cycle. You just need to modify this thing. Okay, multiply by will be still remaining at 2, but you can always modify the duty cycle. You can put 30 over here. So that will define your rising edge, and the remaining will be for your fall edge. Okay, so this was the multiply by circuit, was pretty simple. So that's all we had from the generated clock point of view. In the next or in the upcoming videos, we'll be coming up with more frequently asked interview questions and try to solve that. So let's try to bring up some more questions from the next video. Thank you.